follows extensive work. People have focused for almost the last 20 years about the calculation of the stress intensity factor around a natural crack. And the remark number one that I'd like to say is that from a single experiment, which is here, a rhombus notch. Of course, there was a previous crack that you have seen that it was an abrupt crack initiation. That is all what Dominique has been addressed and many others after here. And from this single experiment, you can address both configurations, the one with the V notch or a square notch, as we're going to see later. And if you follow up this crack growth, because it's similar to a DC-DC experiment, then we can address continuously the propagation of natural crack. In single experiment, we do address the V notch configuration and the natural crack configuration. And for the last 20 years, we have focused on this thing that I will briefly recall. So in the past, I've been working with, for instance, Julien Rotoré. We had been machining a natural crack, which is not trivial in the single sample, and doing micro-scale digital image correlation. We were loading, for instance, a sample of PMMA like this. The crack is here. We captured the displacement field around it, and the idea was then to try to identify the cohesive model for the failure mechanism in this material. Cohesive model is very simple in when we present it. It's the traction separation law that is preceding the crack nucleation. And the point is that here, looking at the local displacement field is not reliable, whatever the degree of refinement that you can have with your spec. So the idea is that not looking at the displacement field here, but looking at the closed cracked fields. And looking at the closed cracked fields, you have the Williams series with the mode 1 and mode 2 terms and the different contributions that are reported here. And later we're going to focus only on the first term. But all the additional terms, the regular terms, are accessible with digital image correlation. With the notch configuration, we will stack here. But in the near future, I hope we will be able to address all the equivalent terms here. So you look for a shape of the displacement, a form of the displacement field that looks like this. And there is a little, so that is done already from the late 80s by this community. And people in France around François Hilde and Stéphane Roux have observed that to have this displacement field, you have to have a clear knowledge of where is the crack. And the crack is not easier to identify experimentally. So there is a recurrent expression here that allows you to detect the position of the tip by looking at the K1, the standard K1 term, and the first, they do call it, do means Hilde and Roux, first super singular term that in the Dominique language is the dual mode. But having this, you mask here the non-reliable displacement field, you address this quantity, you invoke those papers, and you're able to measure the stress intensity factor under the mode 1 and under the mode 2. There is a little bit of a mode 2 because of the loading conditions. So what is the message here? The message is that even a simple looks under pure mode 1, realistically or in real life, it can be slightly different. And you can address this. What is reported here, the position of the crack tip, and we have shown with Julien Rotoré that this provides information about the development of a processor. Having this information here, you can recast this in this way. So basically you have a loading, nothing happens, you have the natural crack. Then here you could show that this is the development of the processor, and then the crack runs. But that is already old stuff, 30 or 10 years ago. We did show that having the previous material, we were able to identify the cohesive zone profile that is in here. So all these works, they have inspired us. It was reliable with it was consistent with other measurements. In here, we're going to be inspired by this and to extend this to measure around a notch with an angle here of 90 degrees, the generalized stress intensity factor. So we choose in this example the square holes. That was done also in connection with the work of with the group of Alberto Sapora. But we are going to focus on this here. So maybe this works. Look. What do you see here? You see that at the first, this was the first corner that you have to believe. There is an angle here with respect to this segment of the square angle. And there is another one slightly different on the left. So, if it was in pure mode 1, the track would have run along this trajectory here. And distinctly than what has been showing Alberto Sapora this morning, when you do perfect finite element calculation, you cannot distinguish between one of these 4 corners. And actually, in real life, there is one that at which the crack initiates preferentially. This means that there is a slight difference between corner here, corner there, and so on. We notice here also that there is a different deflection on the first crack and on the second crack that did not grow simultaneously. So, So that is then we come to the point. We are going to look at real tensile specimens of square holes, and the size of the square holes are different. We are going to come out with some background of the calculation of the generalized dense intensity factor from the DIC displacement field, then how to extract, how to run AP calculations, a few words about the couple criterion if time is left, and then some outcomes. So this has been shown this morning by Alberto. What do you see here? So the sample looks like this, different size of the H and different width. So actually, the size of the corner ranges from 15 down to a little bit more than 1 millimeter. And the width of the specimen is as much as we could for this wide square hole. And the ratio between W and C, according to Alberto this morning, if it was larger than 8, it would be, the median could be considered infinite. I used to consider 5, but that's a matter of point of view. But you see that here on the left, we are far from the conditions to have an infinite median. This means what? This means that boundary matters, and boundary influences the displacement field. So this promotes and this motivates us to work with observed displacement field. But then you do what? Then you do an experiment, it's very simple, it's a test machine, the plate of PMMA with a square hole. We cut the PMMA, then we perform a heat treatment to remove potential stresses that came with the machining process. And this is supposed to be a neat, at least free of initial stresses, plate of PMMA. Here is the camera, that is the speckle. Speckle is all the same for all the samples. We will see that this has a consequence later on. And using Julien Rétoré digital image correlation software, we extract the displacement field, UY in this case, UX, and UY in the second case. And then from this we do what? But from this, we try to work out with extracting, so assuming the displacement field of this shape, so a constant term, and kr to the power lambda, lambda being distinct than 0.5 in the case of a notch, and it has been tabulated and shown this morning by Alberto Sapora. And you have to distinguish the mode 1 and the mode 2 with an exponent, lambda 1 and lambda 2, which are different, as presented this morning. So what do you define? You define the direction of the dissector and its perpendicular direction. From each corner, so here the corner, you can identify it more or less accurately. You define the distance R with respect to the notch tip and the angle phi here to make it distinct than a theta. So you do that for corner 1, 2, 3, and 4. And you assume that the displacement field has this shape. Then you go on through the books of Leguillon and also Zohar Estevez, very instructive. What I want to say here is that the analytical expressions of the displacement field are all known. And this will be used as reference displacement field for the later calculation. We also know that for the 90 degrees notch, lambda 1 is close to 0.5 and lambda 2 close to 1. These are the elastic modeling. So knowing the displacement field and assuming that the material is linear, elastic, and isotropic, you can derive the stress field. Again, all the components are known. You just have to verify that is actually the material under consideration really linear elastic, but it is linear elastic up to a point. Then there is a little bit of non-linear elastic effects. So up to this magnitude of the stress, it is reasonably acceptable. You also derive the Poisson ratio that was, of course, from an unnotched sample for the material under consideration. So with this, you have everything to go on through the GSEF machinery, which involves an interaction integral capital C. All the details of these are in the Leguillon Sanchez Valencia book. And what do you have here? You have a known displacement field and a kinematically acceptable order, and you can show that this integral is, Dominique Leguillon has shown that this integral is path independent. So what we are going to use here is that the displacement, capital U will be the displacement field from DNC or from finite element calculations, as in the paper of Doitrand. And phi is a solution that is going to satisfy the equilibrium and the boundary conditions. So phi is going to be for us the reference solution. Some comments about these two parameters are provided here. If you assume the reference solution R to the power alpha, U alpha, and another exponent beta, U beta, this interaction integral is nil if beta is distinct to alpha, and is distinct than 0 if beta equals minus alpha. So if you consider in our solution the positive exponents that we see here, beta equals to minus alpha is called the dual mode. And the dual mode is, in the spirit of Heed, Roux, and co-workers, the super singular mode. But in fact it is very, very similar. So what are we going to express? We have the measure displacement field, and by assuming this auxiliary field, somehow we are able to derive the generalized stress intensity factor that is here. Running these calculations across different paths allows you to, from the calculation of capital C with the real displacement field and the reference solution, to extract the generalized stress intensity factor. So it is a matter of what? All of these things, they are known. This is measured. And you need to calculate, you have the displacement field, strain field, stress field, to calculate this capital C along different trajectories. And you come out with the truncated, generalized William expressions of this shape. So before going to the experimental calculations, we do what? We do a proof of concept from finite element calculations. So the proof of concept is here. This is the tensile bar loaded into this direction. we have the finite element displacement field, and we perform the previous methodology for different whole size. And what do we see here? That is the generalized stress intensity factor for the mode 1 and the mode 2 that is shown to vary with the whole size, as it was reported this morning by Alberto Sapora. What we see here is that the mode mixity, and as mentioned this morning by Alberto Sapora, it is also dependent on the structural parameter that is called here L max, in this case capital. It should not be C. Okay. Say it is a phi, or say it is another. So it is this one. The mode mixity here goes up with a reduction of the whole size. So we come out with results that were already known analytically, but that we can recover numerically. Second calculation, we have seen that there might be the propagation of a crack, and then what is this corner feeling? This corner is feeling something that implies a little bit of tension and a little bit of a bending. So having this changes a little bit the distribution of the generalized stress intensity factor K1 and K2, the proper exponent here, and a different variation with the whole size and a different mode mixity. So when we analyze crack propagation at the first corner and then the crack propagation at the subsequent corner, it is necessary to consider the real geometry and the real displacement field. These are going to be distinct than the previous one. But it works for finite element calculation. Then what happens with DIC? What happens is shown here. Here it is the mode 1, here it is the mode 2, and here it is the calculation of the mode mixity. What do you see here? Black, blue, green, red corresponds to the fourth column, to the four column. And a little bit of a gray thing that corresponds to what? The calculation on repeated and distinct path integrals around each notch. So we are aware that performing a line integral with DIC calculations can come out with some scattering. And it would be preferable to have not a line integral but a surface integral in 2D. And that we are working on, that we are thinking on. But still, by performing repeated calculations of this line integral and taking the average, it is for us reasonably acceptable. So that is for K1, for K2, and for the mode mixity. If the speckle is small with respect to the size of the square hole, in this case, we have to admit that it is a little bit more scattered, that it is a little bit more reliable. So how can we improve this? By improving the scatter, first. And second, by transforming this line integral into a surface integral. Still, for the mode 1, it is reasonably, we think, acceptable as it goes here. For the mode 2, it is slightly different. And for the mode mixity, it is really somehow a little bit questionable, at least at the beginning. So with this, we do what? If this corresponds to the onset of crack propagation, we can estimate the critical generalized stress intensity factor and work on that. You have seen all of these coupled criterion, energy release rate, and stress base that have to be fulfilled at the same distance here for the abrupt crack growth. This can be recast in this form that has been presented this morning by Alberto Sapora, for instance, and you have the connection between the critical generalized stress intensity factor, materials parameter GC and sigma C, and something that depends on the load. So you work on that, and one condition is that the crack deflection angle theta is that which is going to maximize the release energy rate, or equivalent minimizing the KC. So, doing that, you can compare the finite element calculations, the experimental work, and the match asymptotic predictions, and the comparison is fairly acceptable. And this is just, these are my conclusions, I will end with this, but this is just to show that nowadays it is possible to expand all the digital image correlation tools to the analysis of V0. In my opinion, it has not been done because depending on the angle, the field that you are looking at is distinct. But this is thing that we have in mind with Julien Rétoré, and that hopefully in the near future will be implemented. And with this, I thank you for your attention.
Questions, yes? I was a bit surprised that when you extracted the stress intensity factors from the experimental results, apparently you did not use, you extracted mode 1 and mode 2, and you did not seem to take advantage of the symmetry properties of the modes. I mean, mode 1 is symmetric, mode